Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. So in this specific discussion, we are going to look at one of the decay processes, which is electron capture. And this follows our previous videos that we have done on specific concepts which basically fall under the category of radioactive decay. And this, of course, entailed the concept of alpha decay that we have mentioned, which basically we said it's the release of a helium nucleus, or the formation of a helium nucleus with a daughter nuclei, which are going to be formed after an alpha decay. And then we said that there's another category of radioactive decay process that we refer to as the beta decay. And this basically, we divided it into two branches for the beta positive and the beta negative decay processes. Now, in this specific case, we had mentioned and said that this it refers to the concept of a positron emission, and this one is referred to as negatron emission, respectively. This particular case also, we have mentioned the concept of gamma radiation, and we say that the concept of gamma radiation basically occurs in order to try and stabilize radioactive isotope from a higher excited or excited state of an energy to a stable one. So in this particular case, there's a concept of electron capture, which is also going to be part of the decay processes which are going to be experienced in order to attain this concept of stability. Now, basically, the concept of electron capture is going to occur whereby inner orbital electrons are going to be captured, and this basically is going to lead to the formation of a neutrino and gamma rays. And we're going to illustrate this one in terms of a nuclear equation so that we can be able to understand this specific process. Now, if I can be able to give an illustration of one of the examples, we're going to see that this is going to be a transition from carbon 11 to another nuclide, which is going to be boron. And in this specific illustration, therefore, I'm going to show this process. Perhaps we just use this. So if you have a carbon 11 isotope that is transiting through the process of electron capture to another daughter nuclide, which is boron 11, this is going to be accompanied by the formation of what we call a neutrino, which we have indicated now in some specific videos whereby we had discussed, or in rather in our previous videos where we had looked at some of the decay processes. Given this notation to imply what we call anti-neutrino, and this is the neutrino in this specific discussion. So we're going to see the difference between the V with a bar, which is anti-neutrino, and the neutrino in these two specific illustrations. Now, in electron capture, we are going to have this formation of a nucleid, which is a daughter nucleid, together with the neutrino, given as such. So if you try to look at the nuclear composition of this specific decaying element, which is carbon 11, it's having 6 protons, and of course it's going to contain 5 neutrons. And if we consider that one with respect to the daughter nucleus, then we're going to have 5 protons and then 6 neutrons. And then therefore, if you try to look at the difference between this specific part for the left part of this nuclear equation and the right part, the difference is that there's a transition between this one and this one, whereby there's a losing of a proton and then there's a gaining of a neutron. So basically, we can therefore conclude that the process that is being experienced in this particular case, which you are referring to as the electron capture, is whereby the proton combines with an electron in this specific case, and these are going to lead to the formation of a neutron together with what we call the neutrino, which can be given, or rather this is just going to be 0, 1. So this is going to lead to the formation of course, a neutron and a neutrino, given using that specific equation. So therefore, this is going to create a summary for the process of electron capture, but we're going to look at other aspects, perhaps figuratively using the image of an atom, and in this case, of course, we can just use an overall equation of this specific nature, whereby we're going to have this neutrino or neutrino being just given as such. So in this specific case, of course, as I've said, we can be able to use an illustration of an atom, and we said that we can be able to represent an atom using the shells from our quantum numbers. I've mentioned the concept of the cells. I'm going to put a link of that specific video in our description boxes, so that we can be able to do a contrast and create a difference between these. So if this one is a nucleus, then therefore we're going to have this specific cell as K, L, and M respectively. So those are the shells in just a general illustration for an atom. I'm trying to, of course, illustrate how we can be able to, of course, visualize that aspect of electron capture in that specific case. So we're going to see that there's going to be a preference insofar as these specific cells are concerned. And this is going to be explained as we go by, so that we can be able to have a clear picture how that is going to, or the probability of experiencing this electron capture insofar as these shells are concerned. So we're going to see that the probability of this specific process happening from inner orbitals of the K shell are higher as compared to the outer orbitals like the L and M. And this, of course, is going to explain the higher order shells, whereby there's a decrease of this specific probability, like the case for L and M, as I've said. And of course, we're going to see that this basically is going to have a general effect of trying to have a preference for the inner orbitals of this specific atom. So generally, for higher order orbitals, we're going to see that the probability of experiencing this electron capture is going to, of course, decrease with the increase in the quantum numbers over the electron shells, as I have mentioned. So if we try to look at another example, perhaps an illustrative way, we can try to come up with a way in which you can illustrate this process of electron capture. So I'm going to have this illustration. Perhaps I can use this one for a legible one. So if we have this specific illustration, and therefore we can, so we have this specific illustration, we can just have this one illustrated as this, whereby there's a combination of a proton together with an electron, and these are going to form a neutral, of course, a particle, which we have said is a neutron, together with the neutrino, which we are given as that. So therefore, this is one of the ways in which you can just summarily, in a summary form, try to illustrate this specific process of electron capture. And as we have said that this specific process is going to be, of course, competing with another process that we had mentioned earlier, which was a positron emission in what we refer to as a proton-rich nucleus. And therefore, we say that when these subatomic particles or the nucleons are having a ratio that is, of course, odd one, then therefore there is going to be a tendency to increase the absence of some of the particles in order to try and create that balance. So therefore, for a proton-rich nucleus, then therefore there's going to be a tendency of formation of the neutrons, so that that sense of instability is going to be, of course, catered for. So in this specific case, of course, that is going to give us a summary of the concept of electron capture. And of course, we are going to see them in a summary form so that we can be able to contrast it with other processes that we have already discussed in this specific respect. So I'll just try to look at this and make a summary of the four processes that, or a number of processes that were discussed for these various decay processes, so that we can be able to see a contrast and try to create, of course, the relative differences between one from another. So catch us in our next video, which is going to be a final bit of it, and which is going to form a summary of these specific decay processes. So that is it for now, guys. Bye, God bless.